Welcome! In this session, we'll explore an interesting problem titled Sorting the Sentence. This challenge will test your skills in string manipulation and sorting. Let's dive right into the details and learn how to solve it step by step. The problem asks you to reconstruct a sentence from a scrambled input string. Each word in the scrambled sentence has a positive integer at the end, which tells you the original position of that word in the sentence. Your goal is to use these numbers to reorder the words and return the original sentence. The input is a single string S, where words are separated by spaces, and each word ends with a digit indicating its position. The output should be the reconstructed sentence, with the words in their correct order and without the trailing numbers. For example, if the input is S equals is2 sentence for this one A3, your task is to reorder the words based on their positions indicated by the numbers and return the sentence in its original form, which would be this as a sentence. Looking at the first example, we start with the input string S equals is2 sentence for this one A3. Here, each word is paired with a number indicating its position in the original sentence. For instance, is2 is in position 2, sentence 4 is in position 4, this one is in position 1, and A3 is in position 3. To reconstruct the sentence, we sort the words based on these numbers. When we rearrange the words in the correct order, we get this as a sentence. Notice that the numbers are removed in the output, leaving only the clean sentence. In another example, the input string is S equals myself 2 me 1 I 4 and 3. Here, the words in their positions are as follows: myself 2 is position 2, me 1 is position 1, I 4 is position 4, and in 3 is position 3. After sorting the words by their positions, the sentence becomes me, myself, and I. Again, the output contains the words in the correct order, and the numbers are removed. For a simpler case, if the input is S equals word 1, the string only contains one word 1, where the number at the end indicates its position. Since there's only one word, the output is simply word without the number. To summarize, when handling a single word like S equals word 1, the number is removed, and the output is just the word itself, word. The constraints on the problem ensure that the input will always be valid. The string S has a length between 1 and 200, with 1 to 9 words. Each word contains lowercase English letters followed by a single digit between 1 and 9, and the positions are unique, so there's no need to handle duplicates. You also don't need to worry about extra spaces, as the input will always be cleanly formatted with words separated by a single space. Edge cases to consider include inputs with only one word, the shortest possible input like A1, and ensuring that longer strings up to the maximum length of 200 are processed efficiently. By following these constraints and sorting the words based on their positions, you can reliably reconstruct the original sentence. To solve the problem of reconstructing a shuffled sentence, one intuitive approach we considered is a brute force method that involves sorting with manual parsing. The key idea here is to use the trailing digit at the end of each word to determine its correct position in the sentence. The process begins by splitting the input string into individual words. For each word, we extract the trailing digit, which gives us the intended position for that word. Next, we sort the words based on these extracted positions. After sorting, we remove the trailing digit from each word to clean it up. Finally, the clean words are joined together in the correct order to form the original sentence. While this method is straightforward, it has a time complexity of n log n, due to the sorting step, where n is the number of words. It also requires n space to store the sorted words. A major trade-off is that while it's simple to implement, sorting might be unnecessary since the indices have a small, fixed range, and this could be optimized further. Now, a more efficient approach is the optimized strategy that avoids sorting altogether by directly placing each word in its correct position. This method takes advantage of the fact that the trailing digits are unique and sequential. The process starts similarly by splitting the input string into individual words. Then, we create an array of size n, where n is the number of words, to store the words in their correct positions. For each word, we extract the trailing digit to determine its position and place the word, excluding the digit, into the corresponding index of the array. Once all the words are placed, we join the words from the array to reconstruct the original sentence. This approach achieves linear time complexity, n, since we only iterate through the words once, and it still uses n space for the result array. The key insight here is that the sequential nature of the indices means sorting is unnecessary, allowing us to achieve faster execution. While it requires slightly more effort to implement compared to the brute force method, it's significantly faster, especially for larger inputs. Given these considerations, the optimized approach of direct placement is the clear choice for this problem. It avoids the overhead of sorting and leverages the problem constraints effectively. Specifically, the trailing digits being unique and sequential makes direct placement not only efficient but also intuitive. With a linear time complexity of O(n), this method is well suited for handling large inputs. On the other hand, while the brute force approach works, it unnecessarily complicates the solution by introducing sorting, which increases time complexity to O(n log n). Since both methods are straightforward to implement, the optimized approach stands out as the better option due to its efficiency. The key realization, or the aha moment, was recognizing that the numbers at the end of each word could directly map to indices in the resulting sentence. By leveraging the sequential nature of these indices, we could completely bypass the need for sorting, making the solution both elegant and efficient. In conclusion, the optimized approach is the superior strategy for solving this problem. It is faster, avoids unnecessary computational overhead, and makes efficient use of the problem's constraints. By directly placing words into their correct positions based on the trailing digits, we achieve an elegant solution with minimal additional space usage and a linear time complexity. This approach not only simplifies the implementation but also ensures excellent performance, making it the clear choice for tackling this problem. The problem involves reconstructing a shuffled sentence where each word contains an embedded number that indicates its correct position in the sentence. To solve this, we start by parsing the input string. The input is a single string with words separated by spaces, and each word has a number embedded within it. The first step is to split the string into individual words using the split function. This allows us to isolate each word, making it easier to work with the numbers and the words separately. For example, the input string is 2 sentence 4 this one A3 becomes is 2 sentence 4 this one A3 after splitting. By isolating these words, we can focus on extracting their positions in the sentence. Once we have the split words, the next step is to extract the embedded numbers and pair them with their respective words. This involves iterating through the list of words and identifying the digits within each word. For instance, you can use the isdigit method or a regular expression to locate and extract the numbers. These numbers represent the positions of the words in the reconstructed sentence. By creating pairs of numbers and words, we can organize the sentence logically. For example, the list is 2 sentence 4 this one A3 transforms into 2 is 4 sentence 1 this 3 a. With these pairs, the next logical step is to sort them. Sorting the list of tuples based on the numbers ensures that the words are reordered correctly. In this case, sorting 2 is 4 sentence 1 this 3 a results in 1 this 2 is 3 a 4 sentence. After sorting, the final steps are straightforward. We extract the words from the sorted tuples and join them back into a single, cohesive string using the join method. This produces the reconstructed sentence, such as this is a sentence, which is then returned as the output. This problem provides key insights that simplify the solution. First, understanding the association between words and their embedded numbers is crucial. The numbers turn the problem into a sorting task, where extracting and isolating the numbers becomes the foundation of the solution. Sorting by these numbers guarantees that the words align in the desired order, regardless of the input's initial arrangement. The algorithm is also efficient. Parsing the words and extracting numbers takes O(n) time, and sorting the pairs adds an O(n log n) complexity, where n is the number of words. This ensures the solution handles typical input sizes effectively. Edge cases are also considered. For example, if the input contains a single word like word 1, the output remains the same. For already sorted input like this one is 2A3 sentence 4, the algorithm processes it correctly without modifications. However, malformed input, such as missing numbers or improperly formatted strings, is outside the scope of this solution and assumes well-formed input. The solution employs specific data structures to handle the problem efficiently. First, a list of strings is used to store the split words from the input string. This allows easy traversal and manipulation of individual words. Next, a list of tuples is created to pair the extracted numbers with their respective words. This structure provides a clear association between positions and words, making the sorting step straightforward. For example, the list of pairs might look like 2 is 4, sentence 1, this, 3, a. Finally, the output is a single string reconstructed from the sorted list of tuples. This matches the required format of the problem. To optimize the process further, regular expressions can be used to simplify the number extraction, such as with research, or \d plus, word. Additionally, sorting the list of tuples in place reduces memory overhead, making the algorithm more efficient. Analyzing the complexity of the algorithm, the time complexity involves multiple steps. Splitting the string into words takes n, where n is the number of characters in the input. Extracting numbers from the words takes m, where m is the total length of all the words combined. Sorting the list of tuples involves k log k, where k is the number of words. Finally, joining the words into the final string takes m. Combining these, the overall time complexity is n plus m plus k log k. For space complexity, storing the input string requires n, while the list of tuples uses k, where k is the number of words. The reconstructed string also requires m space. Thus, the overall space complexity is n plus k. This ensures the algorithm is both time and space efficient while solving the problem effectively. This solution defines a class solution with a method sort sentence that takes a single input string s. This string represents a shuffled sentence where each word ends with a number indicating its correct position. The first step is to split the input string into a list of words using the split method. This divides the string into separate components based on spaces. Next, we create an empty list called sorted_words with the same length as the number of words in the input. This list will be used to store the words in their correct positions. The algorithm then iterates over each word in the input list. For each word, it extracts the positional index from the last character of the word using word-1. This index is converted to an integer and adjusted to 0-based indexing by subtracting 1. The word itself, excluding the last character, i.e., the number, is stored in sorted_words at the appropriate index. Finally, all words in sorted_words are joined into a single string using .join, sorted_words, to reconstruct the original sentence. This string is returned as the output. The solution ensures correctness by systematically placing each word in its proper position, and handles edge cases such as varying sentence lengths and different word orders effectively. This is the Java implementation for LeetCode problem number 1859, sorting the sentence. The logic mirrors the Python solution, using Java-specific constructs like arrays and character manipulation. Key steps include splitting the input string, extracting indices from each word, and placing words in their correct positions in a new array. Finally, the sorted words are joined back into a single string and returned. This implementation handles type declarations, array operations, and string manipulation in Java. To solve the problem, we start with an input string, in this case, is 2 sentence 4 this one a3. The first step is to split the input string into individual words using the split method. This gives us a list of words, where each word ends with a number indicating its correct position. So, the variable words holds the value, is 2, sentence 4, this one, a3. Next, we prepare for sorting by initializing a list called sorted_words of the same length as words, but filled with empty strings. This list will eventually hold the words in their correct positions. At this point, sorted_words is, With the setup complete, we proceed to process each word to place it in the right position within sorted_words. Starting with the word is 2, we extract the positional index by taking the last character, converting it to an integer, and subtracting 1 to get a 0-based index. This gives us an index of 1. We then place the word, excluding the index, into the correct position in sorted_words, so sorted_words 1 equals is. Now, sorted_words becomes is, Next, for the word sentence 4, we extract the index, which is 3, and place the word sentence at this position. The updated state of sorted_words is sentence. Then, for this one, the index is 0, and the word this is placed at the beginning of the list, making sorted underscore words equal to this is sentence. Finally, we process a 3, where the index is 2. Placing the word at this position results in sorted underscore words becoming this is a sentence. With all the words placed in their correct positions, the next step is to combine them into the final sentence. We use the join method to concatenate the words in sorted underscore words, separating them with spaces. The result is the output string, this is a sentence. To further illustrate the process, let's look at another example. This time, the input is myself 2 me 1 I 4 and 3. First, we split the string into words, resulting in words equals myself 2, me 1, I 4, and 3. We then initialize sorted underscore words as an empty list of the same length, which is comma comma comma. Now we process each word to reorder them based on their indices. Starting with myself 2, we extract the index, which is 1, and place the word myself at this position in sorted underscore words. This makes the state of sorted underscore words, myself, comma. Next, for me 1, the index is 0, so we place me at the beginning of the list, resulting in sorted underscore words equals me, myself, comma. Then, for I 4, the index is 3, leading to I being placed at the end of the list. Now, sorted underscore words becomes me, myself, I. Lastly, for in 3, the index is 2, so we place n at this position, completing the list as me, myself, and I. Joining these words with spaces gives the output me, myself, and I. Let's consider one final example where the input is 1 1. Here, the process is simplified because there's only one word. Splitting the string gives words equals 1 1, and we initialize sorted underscore words as. For the word 1 1, we extract the index, which is 0, and place the word 1 in this position, making sorted underscore words equals 1. Joining this single word results in the output 1. This example highlights how the solution handles even the simplest cases efficiently. Next, we initialize the sorted underscore words list to hold placeholders for all the words. The size of this list corresponds to the number of words, denoted as k. Then, we process each word in the words list using a loop. Placing the word into its correct position in the sorted underscore words list is also O1. Since there are k words, this loop runs in O, k, which simplifies to O, n. Finally, we join the sorted words into a single string using .join, sorted underscore words. To analyze the time complexity of this solution, we break it down into its individual steps. First, the s.split operation scans the entire input string to identify word boundaries, which takes O, n, time since it processes each character once. Since k is proportional to the input size, this initialization also takes O, n, time. For each word, extracting the last character, converting it to an integer, and removing it are constant time operations, O1. This operation depends on the total number of characters, which is at most n, making it O, n. Adding up these steps gives us a total time complexity of O, n, plus O, n, plus O, n, plus O, n, which simplifies to O, n. Now, let's consider the space complexity of the solution. The words list stores all k words from the input string, requiring space proportional to the input size, or O, n. Similarly, the sorted underscore words list stores placeholders for the same k words, so it also requires O, n, space. Temporary variables like word and index are used during processing, but these only consume constant space, O1. Since we're not using any additional data structures or recursion, the total space complexity is O, n, plus O, n, plus O1, which simplifies to O, n. This shows that both time and space complexities scale linearly with the size of the input, making the solution efficient. When comparing this solution to a naive approach, the difference becomes clear. A brute force method might repeatedly scan the list of words to find the next smallest index, which would result in a time complexity of O, k squared, as each pass involves scanning k words. In contrast, our solution achieves O, n, time by processing each word exactly once. For the best, average, and worst cases, the algorithm's performance remains consistent. Since the operations performed for each word are independent of the input structure, the time and space complexities are O, n, in all cases. Finally, the mathematical reasoning behind the big O notation confirms this efficiency. Splitting the string, initializing the list, iterating through the words, and joining the sorted list each contribute O, N, and their sum remains O, N, after ignoring constants. Similarly, the space complexity is dominated by the memory used for the words and sorted underscore words lists, each requiring O, N. Altogether, this makes the solution optimal for the problem, with both time and space complexities being O, N. When solving this problem, there are a few common mistakes to watch out for. First, not handling edge cases can lead to issues. For example, if the input string is empty or contains just one word, your solution might throw an index out of bounds error or produce incorrect results. This happens because edge cases often aren't explicitly tested, so it's crucial to account for them in your code. Another pitfall is sorting words without properly extracting their positional numbers. If you don't parse these numbers correctly, the ordering of the words will be off. Remember, the sorting logic depends entirely on accurately identifying the embedded numbers in the words. Lastly, modifying the input string directly is a mistake because strings are immutable in many programming languages. This means changes to the original string can lead to inefficiencies or unintended behavior. Instead, work on a processed list of words for a cleaner and more reliable approach. Now, let's consider other inefficiencies that can crop up. One issue is using overly complex parsing methods, like nested loops or multiple traversals, to separate numbers and words. This kind of approach unnecessarily increases the time complexity of your solution. Instead, aim to extract both components in a single traversal to keep things efficient. Another mistake is ignoring space complexity. For instance, creating multiple intermediate lists when a single list or dictionary would do the job leads to higher memory usage. This becomes particularly problematic with larger inputs, where optimizing space usage can significantly impact performance. Always strive to minimize both time and space complexity to make your solution scalable and efficient. In an interview setting, there are some important insights to keep in mind for this problem. Recognizing the pattern of shuffling and reordering is crucial. This means mapping words to their positions based on the embedded numbers, which is the foundation of your solution. Aim for optimal parsing by extracting both the word and its positional number in a single pass through the input string. This demonstrates your ability to write efficient code. Additionally, be prepared to discuss trade-offs with your interviewer. For example, using a dictionary can make the code more readable, while a list of tuples might slightly improve performance. Finally, always clarify edge cases with your interviewer. Ask about scenarios like empty strings, single-word inputs, or inputs where the numbers are missing. This shows that you're thorough and can anticipate potential pitfalls. If you want more practice, related problems like LeetCode 937, 791, 451, and 68 also involve reordering or string manipulation, making them great for sharpening similar skills. Finally, let's explore some alternative approaches and their trade-offs. Using a dictionary is one option where you store the positional number as the key and the word as the value, then reconstruct the sentence. This is straightforward and intuitive but requires extra space for the dictionary. Another method is tuple sorting, where each word is paired with its positional number in a tuple, and then the list of tuples is sorted. While this is efficient with a time complexity of O, n log n, it might be less clear or intuitive to some developers compared to a dictionary-based approach. An in-place rearrangement method is another alternative, where you directly modify the input list. This reduces space usage but can be error-prone and harder to debug. Lastly, there's the two-pass approach, which involves extracting the numbers and words in one pass and then reordering them in a second pass. While this is slightly less efficient, it's easier for beginners to implement. Each approach has its strengths and weaknesses, so choose the one that best fits the problem constraints and your familiarity with the technique. Great job! We've successfully solved and analyzed the sorting the sentence problem. Remember to practice similar problems to reinforce your understanding. Thank you for joining, and I'll see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!